Welcome to UBG Bytes. Today we're diving deep into Flutter. You know, that open source UI framework from Google that seems to be everywhere now? What's really interesting is how you can write code once and, well, it just works natively on Android, iOS, desktops, the web, pretty much everything.
Exactly. And our mission today really is to get a good handle on why Flutter's taken off like this, especially how it manages that cross-platform trick.
Yeah.
Then we'll get into some of the research on reverse engineering these Flutter apps, see what makes them tick and, what the security implications might be.
Right. And we've got some solid material to work with. Guides from Now Secure on OWASP MES, Osterlab's work on Flutter reversing, the OWASP POP 10 specifically for Flutter M3, Flutter's own security docs, and Waverly's pros and cons piece. Okay, so let's start at a high level. Why Flutter? Why are so many developers flocking to it?
Well, the big draw, as Waverly points out, is that single code base. You write it once, run it everywhere. Think about the efficiency gain there. No need for separate iOS and Android teams doing the same thing twice, saves huge amounts of time, and naturally, money.
Yeah, that single code base thing sounds like a massive win right off the bat. And Waverly mentioned it speeds up getting apps out the door too, right? Faster time to market.
Definitely. But it's not just about speed of development. The user experience is key too. How do the apps actually feel?
That's the crucial part, isn't it? Do they feel clunky or genuinely native?
And that's where Flutter really scores well, largely thanks to its Skia rendering engine. It doesn't rely on web views or interpreters in the same way some other frameworks do. Flutter compiles that Dart code directly to native machine code. Waverly highlights this. It leads to fast, optimized performance without that laggy feeling.
Ah, okay. So it feels native because, in a way, it is native code running on the device. Osterlab also flagged that performance as a big plus. What else is pulling developers in?
The community is a huge factor. Flutter has this really large active community. So if you hit a problem, chances are someone else has too. And there's help available. That's something multiple sources noted. And Waverly also talks about Flutter's own rendering engine, letting it use platform-specific design languages like Material Design for Android and Cupertino for iOS from that same code base.
That's smart. You get the efficiency and the right look and feel for each platform. Waverly also mentioned hot reload. That sounds useful.
Oh, it's brilliant for developers. You make a code change, hit save, and you see the result in the running app almost instantly. No waiting for a full rebuild.
Wow, okay. That must speed up the tweaking process massively.
Absolutely. It makes iterating really fast. Waverly also touched on some safety aspects like null safety built into the Dart language and how computations run in isolated threads, little things that help prevent certain bugs.
And Dart itself, the language Flutter uses. Waverly mentioned its compilers, AOT and JIT. What's the story there?
Right. So AOT, ahead of time compilation, is what you use for the final release build. It optimizes the code for fast startup and performance.
Yeah.
JIT, just in time, is used during development. That's what enables that hot reload feature we just talked about. Gives you that instant feedback loop.
I see.
And Waverly adds that for web, Dart currently compiles to optimize JavaScript, but they're looking at WebAssembly support down the line too, which could be even faster.
That's quite a package. It seems to tackle a lot of the common headaches in mobile development. And the list of users Waverly mentioned, Google, Alibaba, BMW, eBay, that's serious industry adoption.
Yeah, that kind of buy-in speaks volumes.
Yeah.
Just quickly, Waverly also sketched out the architecture. It's layered. You've got the framework in Dart where developers work. Below that, the engine in CC++ handles graphics, text, that sort of thing. And then the embedder connects it all to the specific operating system.
And the UI itself is built with these things called widgets, right? Reusable blocks.
Exactly, as Waverly explained. Everything you see is a widget.
Okay, good overview. So how does it actually do the cross-platform thing? Take that one Dart code base and make native iOS and Android apps.
That's the clever bit, yeah. As Waverly details, the developer writes the app in Dart. Then the Flutter build tools take that Dart code and compile it specifically for iOS, producing native ARM code, or for Android, producing native ARM or by86 code.
So it's not like running JavaScript in a web view or anything. It's actual native code for each platform.
Precisely. That direct compilation is why the performance feels so native. No bridge, no interpretation layer slowing things down at runtime. And Waverly mentions the AOT compiler again here that's key to getting those optimized fast-starting apps. And like we said, this whole approach avoids needing separate native teams, which is a big cost saver.
Incredibly efficient. Okay, let's switch gears. Let's get into the research Osterlab covered on, well, taking these Flutter apps apart, reverse engineering them. Osterlab mentioned this is still kind of new ground, right? Not as much security analysis work done on Flutter compared to, say, native Android or iOS apps.
That's a really important point from Osterlab, yeah. Flutter's popular, but the security community is still catching up in terms of deep analysis tools and techniques. Makes understanding how to probe them even more critical.
And a Flutter app isn't just one big file, is it? Osterlab broke down the structure.
That's right. According to Osterlab, you typically find three main parts. Whether it's iOS or Android, there's a thin platform-specific wrapper app.
Okay.
Then the Flutter runtime, which is usually a shared library like libflutter.so. And finally, the actual application code, often in something like libapp.so.
All right, let's unpack those. The wrapper. What's its job?
Osterlab says the wrapper is basically the entry point. It talks to the OS, sets up the screen, handles touches, runs the main event loop, that kind of stuff. Platform plumbing, essentially.
In the runtime, libflutter.so.
That's the engine. Osterlab describes it as handling all the core Flutter stuff, rendering the widgets using Skia, providing the core APIs, handling network and file I/O, accessibility, the plugin system. And crucially, it includes the Dart runtime itself to execute your app's code. Osterlab stresses that this runtime is generic. It's the same across different Flutter apps. Your specific logic isn't in there.
Right, it's the machinery, so the unique bits, the app's actual code and UI, that's all in libapp.so.
Exactly. And Osterlab notes this isn't just standard compiled code. It's a custom format bundling the UI layout, the compiled Dart code, and various data objects. They also talk about the Dart snapshot. Think of it like a pre-warmed up state of the Dart virtual machine, ready to run your main function containing your compiled code. And there's a VM isolate, too, holding essential runtime objects.
Okay, self-contained package. So if you want to analyze this for security flaws, what tools or methods does Osterlab say are available?
Osterlab mentions two main approaches, static and dynamic analysis. For static, looking at the code without running it, they mention a tool called doldrums. It tries to parse that custom libapp.so format.
Sounds like there's a catch.
Yeah, Osterlab points out doldrums only really worked with older Flutter versions and isn't maintained anymore. The Flutter format changes too fast.
That highlights the challenge, doesn't it? Analyzing a moving target. What about dynamic analysis watching the app run?
There, Osterlab talks about tools like reflutter. The idea is to patch the Flutter runtime, libflutter.so, while the app is running to extract information, often used with tools like Frida or debuggers like LLDB.
But again?
Again, the same problem. Osterlab notes reflutter also struggles with the latest Flutter runtimes because internal changes broke its patching methods. Keeping up is hard.
So these tools are lagging behind Flutter's own development pace. Osterlab then suggests a different approach might be better, patching the runtime itself.
Yes. Osterlab argues that instead of constantly chasing the file format changes, a potentially more robust way is to modify the source code of the Dart SDK, the tools Flutter uses to inject your analysis hooks there. It's involved. You build your app, get libflutter.so and libapp.so. They have matching identifiers, a snapshot hash. They must match. So Osterlab's process involves finding the exact Dart SDK version used for a specific Flutter release, getting its source code, modifying it to extract info, and creating a patch.
Okay, sounds complex. What's the key step after making that patch to the Dart SDK?
The crucial bit, Osterlab explains, is building your own libflutter.so with your patched SDK. But changing the SDK code normally changes that snapshot hash.
Which would break compatibility with the original libapp.so.
Exactly. So Osterlab says you have to find the script in the Dart SDK build process, usually make version.py, that generates the hash. You modify that script to force it to output the original hash, even with your patches applied.
That's clever. Sneaky, but clever. You preserve the handshake.
Precisely. Then you can apply your SDK patch, build your custom libflutter.so for the right OS and architecture, and swap it in.
Okay, so you've got your custom instrumented runtime. How do you actually extract useful stuff, like function names or classes?
Well, Osterlab mentions reflutter used to patch a class table object, but that's less reliable now as the structure changed. Instead, Osterlab's approach focuses on patching a specific internal function called postload inside something called the function deserialization cluster in the Dart SDK. By patching postload, you can make the dump out details about the functions like their memory addresses into a structured format like JSON as the app loads.
That sounds much more targeted. What about other dynamic analysis, like intercepting network traffic? Osterlab touched on that too.
Yeah, having those function offsets helps target dynamic analysis tools like Frida more effectively. Osterlab also mentions patching the SSL certificate verification function SSL Cryptox 509 session verify cert chain. By patching that, you can basically disable certificate pinning or validation, allowing you to stick a proxy in the middle and see all the HTTPS traffic without needing special certs on the device, though they recommend using an invisible proxy for stealth.
A powerful technique set. And Osterlab also highlighted using metadata from the Dart snapshot itself to help with reverse engineering.
Yes, this is a big one. Osterlab explains the snapshot contains lots of metadata, class names, function names, package structures. By extracting this and feeding it into tools like IDA Pro, maybe with some Python scripts, you can automatically rename many of the functions in the disassembled code. Their example showed it massively reduced the number of anonymous functions, letting you focus analysis on the app-specific code much faster. Helps map out how the app uses the Flutter framework, too.
That sounds like a huge time saver for anyone trying to understand the code. But Osterlab also mentioned Flutter's built-in obfuscation isn't a silver bullet.
Correct. Flutter does have an obfuscate flag, which makes Dart names harder to read. But Osterlab points out the actual compiled machine code isn't heavily obscured. So even with obfuscation, you can often use binary diffing, comparing the obfuscated code against a non-obfuscated build or known framework code to identify many standard Flutter functions. It helps narrow down where the interesting custom code lives.
Okay, so even with these analysis methods, Osterlab suggests there are still gaps, areas needing more work.
Definitely. Osterlab emphasizes that Flutter's relative newness and the constantly evolving Dart AOT snapshot format mean reverse engineering tools are always playing catch-up. Runtime patching is promising, but maintaining compatibility with Flutter's rapid updates is tough. So dynamic analysis capabilities for the latest versions might lag. And while metadata extraction helps, they note we still lack the kind of fully automated, comprehensive decompilers or analysis suites you see for native Android, Java Kotlin, or iOS, Swift Objective-C.
So more deep disassembly work is needed.
Yes, to really get into the weeds of the compiled Dart code and find potential low-level bugs. Osterlab basically says relying on Flutter being hard to reverse engineer isn't a good security posture. Determined attackers can get in.
And they hinted at specific areas for future research, right? Like where vulnerabilities might lurk.
They did. They mentioned looking into memory corruption risks around Dart.fe. That's how Dart talks to native C code. Also, potential issues with Dart.jna Android and Dart.js web interoperability. And things like reflection, reflectables, and serialization were also flagged as needing investigation. It suggests the boundaries between Dart and other environments or complex internal mechanisms are prime areas for security scrutiny.
So if basic obfuscation isn't enough, what should developers really be focusing on architecturally?
Well, that leads us nicely into thinking about common vulnerabilities, like those highlighted by the OWASP Mobile Top 10, particularly the M3 category on insecure authentication and authorization that one of our sources focused on.
Right, because even if reversing is hard, if the basic auth logic is flawed, attackers might not need to reverse engineer much. Let's connect the dots. How do these common mobile vulns apply in the Flutter context, based on the OWASP PM3 source?
The OWASP PM3 article makes it clear. Flutter apps are susceptible to the same auth problems as any other mobile app if developers aren't careful. The reverse engineering techniques we discussed just make it easier for attackers to find those flaws if they exist.
Okay, so what are some classic authentication mistakes highlighted in that OAuth PM3 article for Flutter?
A big one is weak password policies enforced only on the client side. Checking password length only in the app. That's easily bypassed. Server-side enforcement is essential. Another major issue is insecure storage of tokens, like session tokens or API keys. The article specifically calls out not using shared preferences in Flutter for sensitive data. It's too easily accessible on rooted jailbroken devices.
So what's the recommended alternative?
Use the Flutter Secure Storage plugin. It leverages the platform's native secure storage, like Keychain on iOS and Keystore on Android. Much safer.
Makes sense. Don't trust the client. What else?
Missing multi-factor authentication, MFA. Just relying on username password isn't enough these days. The article pushes for things like TOTP authenticator apps, push notifications, or biometrics. But importantly, it warns that client-side biometric checks can be bypassed. Biometrics should ideally unlock a securely stored token, not grant access directly without a server check.
Right. Use biometrics for convenience, but the real security comes from the token and the server. What about session management?
Another common failure point. Things like tokens that never expire or expire after weeks or months. No proper logout functionality. Insecure token refresh mechanisms. OWASP recommends short-lived access tokens, securely stored refresh tokens, and robust logout. And also, don't rely on security through obscurity for internal or test endpoints. Assume attackers will find them.
These all sound like fundamental security errors, yet they keep appearing in the top 10. What about authorization flaws in Flutter apps?
The OWASP M3 article hits on key authorization mistakes too. Broken object-level authorization, or BOLO, sometimes called IDOR.
That's where you can access someone else's data just by changing an ID in their request, right? Like user123 to user124.
Exactly. The backend fails to check if the logged-in user should be allowed to see data for user124. Always need server-side checks for ownership. Using non-guessable IDs like UIDs helps too.
Makes sense. What else on authorization?
Broken function-level authorization, BFLA. This is about accessing functions or actions you shouldn't be able to, like admin functions. Maybe an API endpoint exists but isn't linked in the UI for normal users. Attackers can find and call these directly if they aren't protected by proper role checks on the server. Again, server-side validation of roles based on secure tokens is critical. Don't trust roles sent from the client. And, similar to authentication, ensure any admin endpoints are properly secured, even if they seem hidden.
It really hammers home that server-side validation is king for anything security critical. The OWASP article also mentioned RASP runtime application self-protection and a tool called free RASP. How does that fit in?
Right, RASP is presented as an extra layer of defense. It's tech embedded in the app that actively monitors the environment it's running in. Free RASP, for example, can detect if the phone is rooted or jailbroken, if a debugger is attached, if it's running in an emulator, if the app's code has been tampered with, or if someone's trying to bypass SSL pinning.
So it's like an alarm system inside the app.
Pretty much. Even if your auth is solid, an attacker on a compromised device might try to hook into the app or modify its behavior at runtime. RASP aims to detect and potentially react to that tampering. It makes runtime attacks harder.
A useful defense in depth measure, then. It sounds like the RWASP article provides a good checklist for developers, too.
Yes, it summarizes the key points. Strong policies, server-side secure token storage, MFA, server-side authorization checks for everything, consider RASP, audit all endpoints. Basic hygiene, but crucial. Securing Flutter isn't magic. It's applying these solid principles consistently.
This has been incredibly insightful. We've covered Flutter's appeal, its cross-platform mechanics, the state of reverse engineering research, including the tools and challenges, and tied it back to fundamental mobile security principles from OWASP. So, here's a final thought for you, our listener, to take away. Flutter's growing fast, and the techniques to analyze it are evolving too. Beyond the standard secure coding advice, what proactive steps should developers be thinking about now to really harden their Flutter apps against not just today's threats, but tomorrow's? How do you strike that balance between moving fast with Flutter and building truly resilient, secure applications in this cross-platform world?
That's the million-dollar question, isn't it? As Flutter matures and attackers get more familiar with its internals, just following today's best practices might not be enough. Developers really need to understand Flutter's specific attack surface. Keep an eye on research like Labs, and perhaps think more about architectural defenses, proactive monitoring like RASP, and maybe even custom obfuscation or anti-tampering beyond what Flutter offers out of the box. It's an ongoing arms race.